Welcome my friends, welcome to my next lecture. Now for this lecture my plan is to talk about what is called fundamental theorem of algebra. For that you see that applications of Liouville's theorem will come into the picture to conclude what is or to prove fundamental theorem of algebra. In my last lecture I discussed Liouville's theorem, one of the beautiful theorem in complex analysis, and then many nice problems I have discussed that using Liouville's theorem you will be able to solve those kind of problems. So for today's lecture my plan is to talk about the proof of fundamental theorem of algebra. Before that I will start with one estimate, and once I have fundamental theorem of algebra then I will move another beautiful theorem that is called maximum modulus principle, and then couple of its consequences we will talk about that. Then as an application of maximum modulus principle we will have Schwarz lemma, and at the end if time permits we will have Morera's theorem. Of course for this week I am talking about. Okay, so let me start with the what is called discussion regarding the estimate of a polynomial, which will help us to prove what is called fundamental theorem of algebra. Okay, so as I said, so let me just start with this estimate. So I have kind of discussed a little bit about in my last lecture. So I need this estimate to apply Liouville's theorem to conclude fundamental theorem of algebra. That's what the target. So what I am doing here, so I am starting with a polynomial P. Say suppose you are dealing with nth degree polynomial. Of course coefficients are coming from complex number. Then I will show that a polynomial of degree n has exactly n many roots, and that is nothing but what is called fundamental theorem of algebra. I will give a proof of that using Liouville's theorem. So for that, this is an auxiliary result that I need it to conclude my theorem. Okay, so what is that? So let Pz, which is a nth degree polynomial, now this is a0 plus a1z plus a2z square plus an z to the n, where an is non-zero because I am dealing with a polynomial of degree n is greater or equal to 1. So therefore an should be non-zero, because since I am dealing with polynomial of degree n. Then what is important is that since n is non-zero, so I am saying that there exists r positive large enough such that the polynomial I can bound. So it will have a lower bound, it will have an upper bound. Of course in terms of z. What is that? It says that then absolute of p of z should be greater or equal to half of modulus of n mod z to the power n, which is lesser or equal to modulus of pz, which is lesser or equal to 3 by 2 times modulus of n times mod z to the power n, where mod z is greater than r. You will see I will have the existence of r such that this is true. Okay, so how to do that? So you have to do kind of there is a trick or there is a kind of bit of algebra, and using the what is called inequality I have already discussed in my earlier lectures, you will be able to prove it. So what I am doing is that I am saying that okay, consider a new complex number w which is like this one. What is this? a0 divided by z to the n plus a1 divided by z to the n minus 1 up to an minus 1 divided by z. Suppose you consider this is w. Once I write w is this one, then you can write your polynomial into two parts, because your pz will have a0 up to an minus 1 z to the n minus 1. This is plus an z to the n, right? Now looking at the expression of w, you can say that if I hit w with z to the n, then what will happen? It should be a0 plus a1z up to an minus 1 z to the power n minus 1, because if I so that means you can say that this object, this portion, I can write it like w times z to the n plus an z to the n as it is. Okay, because looking at the expression of w, if I hit it by z to the n, I will get back this expression. So therefore pz I can write it as w plus an times z to the n. So this is crucial to have the estimate. So this is one of the trick you can say. Then what I will do, then I need to estimate my polynomial of z absolute, upper bound and lower bound. So for the upper bound I will use what? This triangle inequality. That means this should be w plus an times z to the n. What is that? This is w plus an absolute, then you have mod z to the power n, then you will have mod w plus mod an, okay, times mod z to the power n. Then I will have to estimate this object to conclude the right hand side. Similarly, I need to conclude, I need to have the estimate lower bound of this one to conclude that one. So that's the target. So therefore, you write w, then you break your polynomial into two parts. That means, or you can write your polynomial into an plus w times z to the n. Then what I will do, I just, because an is fixed, right? So therefore, for the upper bound, you just need to know the estimate of mod w. Then it will give the upper bound of that one. And for the lower bound also, if I know the estimate of mod w, then I will be able to have the estimate of lower bound. Okay, so for that, what I will do, since you will have the expression of w, if I take the absolute, which is the absolute of this one, and which is dominated by bitriangle inequality, mod a naught divided by mod z to the power n plus mod a1 divided by mod z to the power n minus 1 up to mod a n minus 1 divided by mod z. This is just by triangle inequality. That means I am using this fact, modulus of z1 plus z2, which is dominated by mod z1 plus mod z2. That's what I am trying. So from this to this, it's okay. Now I need to estimate this mod w in terms of a fixed number. Like, see, look at in the right hand side, you will have mod n. So that means this portion will give you the estimate what is called mod z to the power n. But for this portion, if I have the triangle inequality, you will have mod n plus mod w. Now mod n is fixed, right? So therefore I need to estimate the mod w in terms of n. But look, in the triangle inequality, I will have estimate in terms of a naught, a1, n minus 1. So therefore I need to estimate the right hand side in terms of n itself. So now how do I do that? And that also follows from this this expression of the right hand side. Why? Because you see, since p is a polynomial, so therefore a naught, a1 up to a n minus 1 and n, these are fixed number. So therefore the denominator or numerator are the fixed complex number. So now look at the denominator. What is the denominator? Denominator is that mod z to the power n, mod z to the power n minus 1 up to modulus of z. Now you see, look at this denominator. If I say that mod z approaches to infinity, suppose it's taking larger and larger value, then what will happen? This is approaches to 0, this is approaches to 0, this is approaches to 0, right? I can do that. Because a naught, a1 up to an is fixed. So therefore if mod z approaches to infinity, each of the component or each of the terms would goes to 0. So therefore I can make this sum is very small if mod z is large enough, and that's the trick I will use. So what I will do, the main important fact is that the right hand side goes to 0 as mod z approaches to infinity, and I need to estimate the right hand side in terms of what is called an, and then I am done. So what I will do, since this is approaches to 0, so therefore I can make this object arbitrarily small if mod z is large enough. Similarly, I will apply the same method here and here. So what I will do, I will make this is less than, say, epsilon. Now epsilon I need a specific number because I need to estimate in terms of this. So what I will do is that you will see in my next slide it is there. So I can make this is some mod an divided by, say, kind of 2n. Because what? So n is fixed. So look, here n is fixed. So n is fixed because it is a polynomial of degree and n is fixed, right? N is fixed. And then what? A naught is fixed. This is also fixed. So what I am varying? I am varying is that mod z. Now if mod z approaches to infinity, this object is goes to 0. So then what I will do, given epsilon, which is mod an divided by, say, 2n, it is a fixed number, let it be epsilon. So what I will do, I will say that this I can make this epsilon if mod z is, say, greater than, say, r naught. I can do that because mod a naught divided by mod z to the power n goes to 0. Similarly, this object I can make less than, again, mod an divided by 2 to the n, but this time it might happen that mod z, I will have mod z greater than r1. So for this one, for the same epsilon, I will have r naught. Maybe for this term, I want to make this is less than epsilon for, say, some r1. Similarly here, I can make this is also less than mod an divided by 2n because it's a fixed number, let it be epsilon for all mod z greater than, say, rn minus 1. So therefore, how many r naught, r1, rn minus 1 you will have? You will have n many. So for this one, given epsilon is equal to mod an divided by 2 to the power n, I can make this object less than this epsilon for mod z greater than r naught. This is for mod z greater than r1. Up to this one is mod z greater than rn minus 1. Then what I will do? Each of the term I can make less than epsilon, but for each term I am having different kind of r naught, r1 up to rn minus 1. So this is a standard trick. What you have to do, take r is the maximum of r naught, r1 up to rn minus 1. So if I take r is the maximum, then each term I can make less than epsilon. Now look at the epsilon. This is mod n divided by 2n, right? But this is kind of adjusting factor, right? Because how many terms are there? A naught, a1 up to n minus 1. The n many terms will be there. So therefore each time, so that means I can make this object is less than n epsilon. But what is n epsilon? N times epsilon is given, na? Mod n divided by 2n. So n will get cancelled. So therefore it should be exactly equal to half of mod n. That's what it is. So therefore I can make this is less than half of mod n for all mod z greater than r, which is nothing but the max of r naught up to r n minus 1. So that's the trick. So if mod w is less than half of n, look here. So this is less than half of n, this is plus mod n. So half mod n plus n, so therefore 3 by 2, and this is nothing but this one. So that means upper bound I am getting, lower bound also similarly you can have it, because you have to use that kind of famous inequality like modulus of z1 minus z2, which is greater or equal to modulus of mod z1 minus mod z2. If I have that one, so this is the kind of greater or equal to part, so therefore if I take the reciprocal it will be lesser or equal to. So that's why you have to use. Maybe in the next slides I have explained everything. Look, so first is that, so you can have the existence of one r which is sufficiently large r such that each of the term I can make this object, and this is true. Why? Because this term goes to 0 as mod z approaches to infinity, because here for fixed k, ak is fixed and n is fixed, so therefore n minus k is fixed, so therefore this object goes to 0. So therefore I am saying that take this is as an epsilon, so I can make this is less than epsilon for all mod z greater or equal to say some rk. Okay, and how many k's are there? 0, 1 up to infinitely many. So you can take r is the max of r naught up to rn minus 1. So therefore I can make each of the object less than epsilon, which is nothing but mod n divided by 2n for all mod z greater or equal to r, or you can say that this is mod z greater than r. You can take r plus 1. So that is also, you can say, suppose this is r2 ideal, so r2 ideal plus 1, this is r, you can think. So therefore all mod z greater than r, I will have this expression. Then by triangle inequality, mod w which is dominated by this plus this up to this, each of the term I can make mod an by 2n, n many terms are there, so n get cancelled, so therefore you will have mod an by 2, and this is true for all mod z strictly greater than r, you can have it. So therefore one hand I have this inequality, perfectly alright. See, that will give you the upper bound, the right hand side. For the lower bound you will have this inequality, mod n plus w, which is greater or equal to, like this is the one I have already explained. So either z1 plus minus z2 you can have it. So this is greater or equal to modulus of mod z1 minus mod z2. Okay. So this is n plus w, which is greater or equal to modulus of mod n minus mod w. Now mod w is already dominated by mod n by 2. So therefore if I take the minus of mod w, which is greater than minus mod n by 2, and that is true for mod all z greater than r. Okay, and this information together will give you that mod n minus mod n by 2. So therefore this object is half of mod n for all mod z greater than r. So therefore now look, for the lower bound I will have modulus of pz, and what is the expression of pz? Look, pz is n plus w times z to the n. So therefore if I take the absolute, so therefore this should be modulus of n plus w times mod zn. Just now I have concluded that modulus of n plus w, which is greater than half of n, so therefore this should be half of n times mod zn. So this is okay for all mod z greater than r. So equality r, you can forget this is greater than r, because you can take r2 ideal is the maximum and take r is the r2 ideal plus 1. So therefore for all mod z strictly greater than r, this is also true. And for the, this is for the upper bound I am done, sorry, for the lower bound greater than, and for the upper bound is the triangle inequality. This is same as this, which is dominated by this plus this. So and keep as it is, and mod w is dominated by mod n by 2, so half of mod n, so therefore this will give you 3 by 2 mod n mod z to the power n, and this is true for mod or z greater than equal to r or strictly greater than r. So therefore finally we will have this inequality. So therefore if I have a polynomial of degree n, that means n is non-zero, so therefore I will have the existence of one number r. If mod z is strictly greater than r, then I will have the upper bound and lower bound of modulus of pz in terms of the coefficients mod n and mod z to the power n. Okay. Now you will see that will help us to conclude the proof of fundamental theorem. Okay. So first observation is this one from the last theorem. What it says is that, it says that once I have this inequality, that will tell you that by using the above inequality that this modulus of pz, it blows up, and hence pz approaches to infinity if at z approach to infinity, and that is true. Why? Because you see in the lower bound, so for the what is called the estimate, since I am kind of trying to conclude that modulus of pz is going to infinity, that means you just care about the lower bound, not the upper bound. So for the lower bound, what we will have, if I have a polynomial, then there exists a R such that you will have modulus of P of Z, which is greater than half of modulus of n times mod z to the power n, and this is true for all odd mod z greater than R. Now you see, this is greater than this one. Now if I take mod z approaches to infinity, then this is a fixed number, na, half of mod n, because it's a polynomial of degree n. So then what will be the behavior of mod z to the power n? It's a polynomial of degree n greater or equal to 1. So therefore if mod z approaches to infinity, the right hand side blows up. Since the right hand side blows up, since this object is greater than that one, so that also blows up. So that's the argument. So by using the above inequality, we have to show that, okay, so what we have proved, mod z is strictly greater than R or greater or equal to R. We will have this lower bound, modulus of Pz, which is half of mod n, mod z to the power n. So therefore you can say that put mod z is equal to R, so this is half of mod n times R to the power n. Then the above inequality is true for every z, right, because it is true for all z greater than R. So therefore in fact if I take mod z is equal to R star, which is greater than R, then also the inequality is true. So therefore I can make this estimate also greater than half of mod n times R star to the power n. If I do that one, then conclude that if R star approaches to infinity, then the right hand side approaches to infinity and hence the left hand side. So this is the kind of mathematical way of writing the object. In fact, it follows from this lower bound, okay. So as R star the number approaches to infinity, that means I am taking larger and larger values of mod z, then the lower bound, that means this is the lower bound, this blows up because mod n is fixed. And since this blows up and modulus of Pz is greater than that one, so therefore modulus of Pz also blows up. So therefore the conclusion is that modulus of Pz which approaches to infinity if z approaches to infinity. That means modulus of Pz approaches to infinity if modulus of z approaches to infinity, and that follows from this inequality. So that is why I need it. So to prove that inequality, I need to conclude that modulus of Pz, if I take a polynomial of degree n, then modulus of Pz goes to infinity if mod z approaches to infinity. Okay, now you'll see it will have some nice observation to apply what is called Liouville's theorem. So now look at, I am in a position to prove what is called fundamental theorem of algebra. What is that? So this is the statement you might familiar with. So if I take a polynomial of say degree n, that means n is non-zero, then Pz has at least one zero, okay. Well, you can say that's that fundamental theorem says that it has exactly n many zeros. Well, if I prove at least one zero in C, then what I will do, I will factorize it, then I can have out of n degree polynomial, you will have n minus 1 degree polynomial, then I will apply this theorem once again to have another factor and so on and so forth. If I do that, then a polynomial of degree n I can factorize into n many what is called simple factor, and each of them is a root and it has exactly n many roots. Of course, it will maybe counting the multiplicities, that means one root might occur not one time, maybe multiple times, okay. So maybe just prove that one, then the statement like a polynomial of degree n has exactly n many roots, this follows from this theorem, okay. So let me prove that one. So start with a polynomial Pz, which is a polynomial of degree n is non-zero. I will prove that Pz has at least one zero in C in the complex plane. So what I will prove? So I will prove it by negations. So what the proof proves is that suppose Pz has no zero. Suppose Pz has no zero, that means Pz is non-zero for all z in C. I mean, it will have no zeros. So now you see, if Pz is non-zero for all z, then it is kind of the first intuition is that, okay, why don't you consider these functions, f of z is equal to 1 by Pz. That will make sense. Because I am assuming I want to prove that theorem, I am going via contradictions. Assume that Pz has no zero, that means Pz is non-zero for all z. So then what I am doing, since Pz is non-zero for all z, I am considering the functions f of z which is 1 by Pz. Now what is Pz? Pz is a polynomial, so therefore it is an entire function. It is analytic everywhere in the complex plane. Cosines of two entire functions, that is also entire functions, because the numerator is constant function 1, it is an entire function. Pz is a polynomial. This is also entire functions, cosines of two entire functions, that is also entire functions, so therefore fz is an entire function. So if I assume the fact that p of z is non-vanishing, that means p of z is non-zero for all z in C, then I can define the functions small f which is 1 by p, which makes sense. And because of the fact that polynomial is an entire function and cosines of two entire functions, so therefore this function is an entire function. Now you see, I will apply what is called Liouville's theorem. Now I have the existence of one entire function. The only thing I need to check that whether I can conclude that this function's f is bounded or not. And for that, in my earlier slides, I have proved something. What is that? If p is a polynomial of degree n, then modulus of pz blows up. That means this approaches to infinity as mod z approaches to infinity. Then what does it mean? Since this is true, then you see I have written here clearly. So therefore you can say that by I need to show that fz is bounded. What should I do? By previous theorem, there exists a R such that this is true, because this is true for all mod z greater than R, right? This kind of things. I have already proved there exists a R such that if mod z is greater than R, then modulus of pz, which is dominated by half times mod n times mod z to the power n. Now then what will happen? You just take the reverse. So if I take the 1 by mod pz, which is dominated by 2 by mod n times Rn, that is also true. If I take mod z is equal to R, that is okay. So that means what I am saying is that this will implies that modulus of fz, which is strictly less than m1, some number m1, I am saying, for all mod z greater than R. In other words, what I am trying to say is that since this approaches to infinity, so this is a kind of mathematical way of writing, but you just look at this argument, that is okay. Now, modulus of pz approaches to infinity, mod z approaches to infinity. Now, what conclusion it will give on functions f? Now, what is modulus of fz? This is same as 1 by modulus of pz, right? Now, if pz approaches to infinity, mod z approaches to infinity, that means what? This is goes to 0 as mod z approaches to infinity. That's what it says, na? If modulus of pz approaches to infinity, then 1 by modulus of pz, this approaches to 0. So therefore, what I am saying is that modulus of fz, this is goes to 0 as mod z approaches to infinity. What does it mean by definition, epsilon delta definition? That means it says that I can make modulus of fz, which is arbitrarily small, so let it be some number epsilon, for all mod z greater than some fixed number r. So therefore, I can make, if mod z is greater than r, modulus of fz is less than epsilon. So this is like one of the mathematical way. From the earlier estimate you will have it. So you will have the existence of one m1 such that I can make modulus of fz, which is less than m1, whenever mod z is greater than r. Now if you look at the pictorially what is going on, so this is my complex plane. This is, say, mod z is equal to r. Then what I am saying is that if mod z is greater than r, that means if z lies here, then I can make my modulus of f dominated by some fixed number. So if z lies here. So but to apply Liouville's theorem, I cannot apply Liouville's theorem here, right? Because to apply Liouville's theorem, you need to bound your functions f on the whole complex plane, right? Here I have a functions f which is entire functions on the whole complex plane, but the bound I am getting here, which is only in this portion, not in here. Now to apply Liouville's theorem, I need to bound my functions f on the full complex plane, but that is also you can do that. So that means what will happen in this one? That means what will happen? So mod z greater than r you will have bound, but what will happen mod z lesser or equal to r? But that also you can do that, because mod z lesser or equal to r, that means what domain you will have? You will have closed unit disk, right? And closed unit disk is a compact set in the complex plane. What is your functions f? F is an entire function, that means it is a continuous function. If I have a continuous function on a compact set, then it is bounded. Oh, that's exactly the fact I am using. Now, since modulus of f, since f is an entire function, so therefore f is continuous, so therefore modulus of f, it is also a continuous function on a compact set mod z lesser or equal to r. Now, if I have a continuous function on a compact set, so therefore I will have another bound m2 such that this is dominated by m2 for all mod z lesser or equal to r. So therefore, if mod z is greater than r, this is bounded by m1. If mod z is lesser or equal to r, this is bounded by m2. So now if I take m is equal to max of m1 and m2, then I will say that then modulus of fz, which is dominated by m, and this is true for all z in C. Okay, so that's the target. So therefore, you should not apply just proving or giving justifications here. You should not apply Liouville's theorem, because you have the bound of your functions f only on the outer portion, that means mod z greater than r. But to apply Liouville's theorem, I need to check that my function f is bounded on the full complex plane. So therefore, mod z greater than r, you will have the bound by using the fact that modulus of pz approaches to infinity if mod z approaches to infinity, right? And on the closed unit disk mod z lesser or equal to r, there I am using my function f is continuous, because continuous functions on a compact set gives a bound. So therefore, if I consider the functions modulus of fz which is continuous on a domain mod z lesser or equal to r, I will have another bound. So I will have a bound m1 on mod z greater than r, I have another bound m2 mod z lesser or equal to r. Take m is the maximum of m1, m2. So therefore, I can say that my function's modulus of f which is dominated by m for all z in C. So now I have an entire function which is bounded. So that then by Liouville's theorem my function's f is constant. Since f is constant, I am saying that p is constant, but which is a contradiction, because I am saying that p is a polynomial of degree n is greater or equal to 1. And why this is a contradiction? Because I assume some wrong assumption, that means pz has no 0, so therefore it will have at least 1 0. So that's the argument, okay. So this is the proof continuation. So choose m is the maximum of m1, m2, then modulus of fz which is less than m for all z in C. So therefore my function's f is bounded. Now my function's f is entered as well as bounded. By Liouville's theorem, fz is a constant function in C. It implies that since f is equal to 1 by p, so therefore p is a constant function, so I am giving, which is a contradiction to the fact that polynomial is a degree greater or equal to 1, so it's never be constant. So therefore, why it is true? Because I am assuming a wrong assumption, so therefore pz has at least 1 0, and this completes the proof of what is called fundamental theorem of algebra. Well, fundamental theorem of algebra, you may say that how I can show that exactly in many roots. To conclude that one, this as a corollary I have written. Look, so I have a polynomial pz, be a polynomial of degree n greater or equal to 1, where n is non-zero, then pz has exactly n zeros counting multiplicities in C. You may think about that this is your fundamental theorem, but also earlier one, if I have a polynomial of degree n greater or equal to 1, then pz has at least 1 0. That's also you can think about what is called fundamental theorem. Now how to prove that one? This actually follows from the earlier one, as I said. Now by fundamental theorem of algebra, if I say the earlier theorem is my fundamental theorem, then since pz is a polynomial of degree n greater or equal to 1, then earlier theorem says that pz has at least 1 0, that means let it be z1. So therefore I can factorize my polynomial p into, I can take the factor outside, z minus z1, so we'll end up with one polynomial q, and what is the degree? Degree is n minus 1. So therefore, where q is a polynomial of degree n minus 1, then what will happen? You apply your earlier theorem for the polynomial q. So now applying again the earlier theorem, fundamental theorem of 2qz, qz has at least 1 0, let it be z2. So therefore I can factorize qz into, if I take out the z minus z2 factor outside from q, I will end up with some another polynomial of degree n minus 2. If I just continue like that, at the end you will have pz which is some constant times z minus z1, z minus z2 up to z minus zn, and where k is a complex constant, and so therefore the polynomial pz has exactly n roots, but here z1, z2, zn might be kind of values could be equal. So that means it is counting multiplicity. That means z1, z2 could be equal to some another complex number. Okay, so that's how. So the proof of what is called fundamental theorem of algebra, very nice applications of what is called Liouville's theorem. So first observation is that you first try to understand, if I have a polynomial of degree n, then first observation is that modulus of pz approaches to infinity as mod z approaches to infinity. But this is the observations, but to prove it mathematically, I need to have the lower bound of the estimate modulus of pz, and then you conclude that yes, modulus of pz approaches to infinity as mod z approaches to infinity. Then you have to prove that theorem. Suppose pz, I want to prove that pz has at least 1 0 in complex plane. Suppose pz has no 0, then what we will do, you say that since assume that pz has no zeros, therefore you consider the functions f is equal to 1 by p. It makes sense. Since p is entire functions, constant function 1 is entire, so therefore f is an entire functions. The only thing is remaining to apply Liouville's theorem. I need to check that whether my functions f, which is 1 by p, which is bounded or not. And again that follows, yes, I can prove that f is bounded because of the fact that modulus of pz approaches to infinity. So if modulus of pz approaches to infinity, that means I can bound my functions f, which is 1 by p. If mod z is greater than some r, it will have one bound, and mod z is lesser equal to r, because of the continuity of f, I will have another bound. Take the maximum, you can bound your functions f on the whole complex plane, apply Liouville's theorem, f is constant, and since f is equal to 1 by p, therefore p is constant, and contradictions. So therefore, if I take a polynomial of degree n, it will have at least one root, and from there by applying what is called induction, not induction, so since it will have one root, so you can take out the factor starting with the polynomial p, take a one factor because of the fundamental theorem, you will have another polynomial which is of degree n minus 1, apply the earlier theorem once again take out one factor. If you continue like that, since it is a polynomial of degree n, you can prove that I can factorize my polynomial into n many factors. Okay, so therefore Pz has exactly n roots counting multiplicities. Okay, so now, so this is like fundamental theorem as an application of Liouville's theorem. Now you will have another beautiful theorem, what is called Gauss theorem, that is also follows from what is called Cauchy's integral formula for derivative I have explained. In fact, I have discussed these things. You will see if I have a functions, I can have the value of the functions at some point by averaging. If I take a point z0, if I take a contour around z0, then by averaging my functions on the contour, I can have the value of my functions in the interior. That is called what is called Gauss theorem or Gauss mean value theorem. So Gauss is a German mathematician who contributed significantly in many fields, so including number theory, algebra, statistics, analysis, differential geometry, geophysics, mechanics, everything. But one of the, like, you can say that this is one of the like beautiful theorem, Gauss mean value theorem in complex analysis. So I have written for more example, you can just more information, so you can have this Wikipedia, there you can have it. Okay, so Gauss had an exceptional influence in many fields of mathematics, science, and is ranked of the history's most influential mathematicians. Okay, mainly he works in many nice works in geometry actually. Yeah. Okay, so that's it. Give you the what is called Gauss mean value theorem. What is the Gauss mean value theorem? Like mean value theorem, you know in real analysis. So that means if I have a functions, then continuous functions are differentiable in open interval, then fb minus fa divided by b minus s, like f prime of xi. This kind of things you are familiar. So similarly, you'll have what is called Gauss mean value theorem. What is that? If f is analytic in a simply connected domain, then which is contains your circle, then the value of the functions at the interior, I can average it out. So that means, for example, you just think about your real analysis. Suppose your functions f defined on a closed interval ab and it is continuous on closed interval ab, differentiable on open interval ab, then fb minus fa divided by b minus a, which is f prime of xi, xi is in the open interval a to b, something like that. So somehow you can see you have an interval a to b, so you are taking the value fb minus fa then by length of the interval. That means somehow you are averaging it. So the value of the functions at b minus value of the functions at a, take the difference divided by b minus a, and you will have some point xi. Okay, so this is nothing but derivative at the point xi. So similar kind of things you can have the Gauss mean value theorem. So it says that now you can think about your complex plane, you have a point z0, and suppose you have a circle. What is that circle? This is z minus z0 is exactly equal to r. So positively oriented. So what I am saying is that you can have the value of your functions at the interior z0 by taking the average of the values of the functions on the circle. Average means, see, I am dividing it by 1 by 2 pi, and then I am integrating. So that means, what is z0 plus r e to the I theta? Z0 plus r e to the I theta is a point on the circle, and theta is running from 0 to 2 pi. That means I am taking all the values on my contour, and then averaging means what? I am taking the integration 0 to 2 pi and then divided by 1 by 2 pi. So that's the meaning of average. So therefore, and that will give you the value of the functions at the point z0. So therefore, what is Gauss mean value theorem? If f is analytic in a simply connected domain that contains my circle, of course that contains the point z0 along with the contour, which is nothing but a circle of center z0 radius r, then I can have the value of the functions at z0, which is 1 by twice pi times 0 to 2 pi f of z0 plus r e to the I theta d theta. Then I am saying that is the value of f at z0 is the integral average. So I am taking the integration, so I am saying the integral average. What is the average of 1 up to n? So you can just add it 1 plus 2 plus n divided by n. So same thing. I am taking the integral average. So that means I am taking the integrations of my value of the functions and the contour, and then I am dividing by the length of the intervals 1 by 2 pi. So that's the integral average. So therefore, that is the value of f at z0 is the integral average of the values of f at point z on the circle. And in fact, I have already proved these things while I was talking about what is called mean value theorem, what is called Cauchy's integral theorem for derivatives, okay, if you remember. So well, that is also straightforward to prove by Cauchy's integral formula. See, what is your contour? Contour is a center jet, you have a circle, center z naught, radius r. Now you know, if I have a circle of center z naught, radius r, then you will have the parameterizations. What is the parameterizations? If I write it as what is called gamma z of theta, which is z naught plus r e to the I theta, theta runs over 0 to 2 pi, that's a kind of parameterizations you know. But now what is Cauchy's integral formula? You know, so Cauchy's integral formula, that means value of the functions at z naught, this is my z naught, this is my contour c. So this is 1 by twice pi I, then integration c fz divided by z minus z naught dz, that I know, that is by Cauchy's integral formula. So I can have the value of the functions at z naught by integrating or by having the contour integrations of this kind of integrand fz divided by z minus z naught. Then what I will do, since I know the parameterizations of circle, I will just open or I will just write this contour integration by the, I use the definitions of contour integrations to conclude that one, okay, because I know the parameterizations. So that's exactly I have done. Since contour C has a parameterizations, so that means since z of theta, you know, this is z naught plus r e to the I theta, then you just use the definitions. What is the definition? Definition, if I write it at g of z, okay, so what is the definitions of contour integration? So this should be integration 0 to 2 pi g of z theta, then z prime of theta d theta. So that's the only thing you have to do. Now what is g of z theta? So that means what is z theta? Z theta is nothing but z naught plus r e to the I theta. So therefore g of z naught plus r e to the I theta. So therefore it should be f of z naught plus r e to the I theta divided by z naught plus r e to the I theta minus z naught. This is the denominator, and then we will have the derivative of z prime theta. That means we will have I times r times e to the I theta, then d theta. And do some algebra. So because this will get cancelled and I will get cancelled, so what you will have this one. In fact, this formula I have already discussed in my earlier lecture as well. So the important part is that, so this is again, that's what I wanted to say, that value of the functions at z naught, which is exactly equal to 1 by twice pi integration 0 to 2 pi f of z naught plus r e to the I theta d theta. Okay, so therefore this is like statement is that this is Gauss mean value theorem. So that means I can have the value of my functions at point z naught is as an integral average of the values of my functions f at a point z on the circle, or c is a contour, which is a contour means which is circle centered at z naught and radius r. So that means if I take the integral average, you will have the value of the functions at z naught. That means if I know the value of the functions on the contour, I can have the value of the functions in the interior at the point z naught. Okay. So I think I should stop here. Okay, so this is like, of course, for Gauss mean value theorem, you just need what is called Cauchy's integral formula. But the earlier one, fundamental theorem of algebra, I have nicely used what is called Liouville's theorem to conclude that. So now I will, in my next lecture, I will talk about another beautiful theorem in complex analysis, that is called maximum modulus principle or maximum modulus theorem. You will see. So this is another beautiful theorem. In my next lecture, I will talk about that, and then later you will see as an applications of maximum modulus principle or theorem, you will have another beautiful theorem that is called Schwarz lemma. Okay. So I think in my next lecture, I'll talk on maximum modulus theorem. So now I think I should stop here. So in my next lecture, I'll start with the statement and some motivations and the proof of maximum modulus theorem or maximum modulus principle. I think I should stop. Thank you.